Hey, geometry students. In this lesson, we're going to be talking about composite transformations. Now, this is going to be multiple transformations in a row. So what we're going to be doing is taking a pre-image, finding the image from one transformation, and then taking that image and finding the image of an image for a second transformation, and then so on and so forth. We could do several transformations in a row. Now, let's think about the transformations we've learned about so far. In the past, we learned how to do translations. That's probably the simplest type of transformation. We learned how to do reflections and we learned how to do rotations. We also learned about another type of transformation, a dilation. Okay. The dilation was a different type of transformation than the other ones because the other ones were all called isometries. An isometry is a transformation that retains the original size and shape of the pre-image. So after we transform it, it's the exact same size and shape that it was before. A dilation is not an isometry because it changes the size of an image while maintaining the shape. Now, one of the things we're going to learn is when we do a composite transformation, when we put two isometries together, two or more isometries together, the result is always an isometry. So what ends up happening is we move the image around or rotate it or reflect it, whatever we're going to do, it's because we're not changing the size or shape of the image in either of the transformations. The final image is still the same size and shape of the original pre image, and therefore, two isometries is still an isometry. We're also going to learn that if we reflect an image over, or we reflect a pre image over a parallel line, and then the second parallel line. Okay, so we're reflecting it over two lines that are parallel to each other. That's a composite transformation because we have to do it twice. The final image is going to be just a translation of the pre-image. And why is that? It's because we're flipping it over once and then we're flipping it back again. And really, if we wanted to, we could have just slid it from the original position to the final position, but instead we did it by reflecting it twice. If we do two reflections across intersecting lines, okay, I want you to picture that for a second. We reflect once across a line and then across another line that intersects it. Our resulting image is going to be a rotation about the point of intersection. So two reflections is the same as a rotation about the point of intersection for the lines. We're going to see that that is the case. We're going to actually witness that. And then this last point is really important. The angle of rotation is twice the angle formed by the intersecting lines. In our last problem, we're actually going to work that math out. All right, let's go ahead and take a look at our practice problems for today. Um, Actually, most of this lesson is just going to consist of looking at the transformations and then discussing what the results of these would be. So we're going to reflect the square over the dashed line and translate it by the vector v. Now I'm going to say this. If this were on the coordinate plane, this would be something that we could do exactly. However, a lot of these transformations, what we're going to be doing is just looking at it on a graph and then sort of eyeballing. You're going to use a ruler anytime that you reflect something. You're going to use a ruler, measure the distance, and then make sure you go the same distance on the other side of the line for all 4 points. But here's the question. Are you going to be able to get a line that's perfectly perpendicular to the line that you're reflecting over? Now, if like AD and BC are perpendicular to the line, it's really not that hard to do on this one. But what if the line is diagonal? Like down here for letter C, is it really possible for you to reflect across line PQ exactly so that your line is perpendicular to PQ when you draw the reflection? It's going to be pretty hard to do it, and you're not going to get it exactly, but you just have to eyeball it the best you can. Okay, so for these ones, when you're drawing them, you have to eyeball them the absolute best that you can. Let's take a look at the answer for letter A. Okay, so for letter A, we begin by reflecting ABCD over the line, And we're going to end up flipping the image over because remember, every point, every vertex is the same distance away from the line, just on the other side. So we'd measure D between D and the line. The same distance on the other side gives us the image of D, image of C, image of A, image of B. Then we have to do our next transformation, which is to move things in the direction of this vector by this distance. So what you do is take a ruler on the image of A and then measure over the same. First of all, you measure vector V, I guess, and then you measure that same distance from the image of A to the left, the image of D to the left, C, B, connect the points, and then here is your image, your composite image after a reflection and a translation. Now, the things that you have to measure, you need to make sure you measure distances when you do a reflection, and also make sure you measure the distance of this vector when you do your translation. Let's take a look at letter B. Reflect the figure across M and then reflect across N. We should end up, according to our rules up here, the composition of two reflection across two parallel lines like M and N should be a translation. So we should end up with the exact same shape RST and the exact same orientation, just slid down below line N. Let's see what happens when we do this. Here's letter B. Notice that the first reflection flips all of our points around. So T is the same distance below M as it was above M. S is the same distance below and above. R is the same distance below and above. But then when we do the second reflection, it flips it back. R is back on top. S is down. It's lower compared to R than it is higher compared to T, right? Or it's closer to T than to R. We'll say that. It's closer to the bottom point than to the top point. That's probably the best way to say it. So notice this shape looks exactly like the beginning shape. It's just slid down below line N. And that's what happens when we reflect twice. Now, this was actually reflected twice. So all of these distances were measured for the first line. And then all of the distances were measured for line N too. Measure from R to N, same distance on the other side. T to N, same distance on the other side. But the end result is the same shape as RST above, just slid down below both lines. All right, let's take a look at letter C. Reflect ABC across PQ, so reflect it this way, and then reflect the image across RS. And what we should end up here is with a rotation. Okay, so AB and the shape should be the same, but A, B, and C are going to be in different positions on the shape. Let's see how this one works out. So we start by measuring the distance from A to line PQ, and then we measure the same distance on the other side to get A prime. Same with B, distance, distance, C, distance, distance. Now we take this image and we're going to do the same thing except across line RS. So C, measure the distance, measure the same distance on the other side. B, measure the distance, same distance on the other side. A. Notice that this is just a shape that's been rotated around the intersection of the two lines. So two reflections is just a rotation. What is the angle of rotation? Well, the angle of rotation is going to be double the angle between the two lines. But which angle do we use? Do we use P? We'll say the center point here is, let's make it Z. Do we use PZS or do we use PZR? Well, here's the thing. Notice that this triangle rotates through PZR, through this angle, and then to the next angle. Whatever angle it rotates through to get to its final position, that's the angle we would need to use. So we would say that the angle of rotation is 2 times PZR. It's the angle it rotated through to get to its final position. Now, we're going to see that math a little bit later. So if that didn't quite make sense to you, sit tight. We'll put some numbers to it. Let's take a look at letter D. Perform transformations on the triangle in the following order. Translation to the right, reflection across a horizontal line, translation to the right, and reflection across a horizontal line. Okay, so we're going to translate it according to V. That means we're going to measure V with a ruler, and we're going to move M that far to the right, L that far to the right, N that far to the right. Then we're going to need to reflect across a horizontal line. I wish the horizontal line was pictured because the horizontal line could be immediately below it. It could run through it. It could be a mile below this triangle in my image. Like you just don't know if there's no instructions given. So we're just going to assume that the horizontal line is pretty close here. Okay, so let's take a look at what happens. We translate over to the right by vector v. Now, I'm just going to say criticism, criticism, criticism. This was moved way further than vector v. Here's a picture of vector v, right? Look how far L moved compared to that vector. Somebody didn't use a ruler. So I'm going to call Saxon Math on this one and say that they should have done a better job. But anyway, we translate to the right, reflect downward. Notice it goes upside down because we choose our horizontal line, and then we measure the distance, measure the distance, measure the distance between L and the line, measure the distance between the line and L prime. Okay, same thing for M. Now we're going to translate to the right by the same amount. At least they did it by the same amount, so they're using a systematic vector. Then we're going to reflect back across the original line. Hey, two reflections across the same line result in the original image. So, because the only other change we made to this was two rotations to the right, notice that LN, that says M quadruple prime, L quadruple prime, N quadruple prime, because we did four different uh, trans- transformations on this. Notice, though, that we could have just moved it to the right twice by vector V because the reflections undid each other. When you reflect twice across the same line, the reflections undo each other. Even if you don't do them in a row, uh, you're still going to undo your original reflection. So that's what it could have just been a translation to the right by whatever 2 times vector v was. All right, and then letter E. To create a new logo for a sweatshirt, a designer reflects the letter T across the line H. This image is then reflected across line J. What single transformation could move the letter T from its starting point to its final position? All right, when we rotate across two intersecting lines, what do we call that? Um, Remember, the single transformation that we could have used for letter E is a rotation. Because when you reflect across two intersecting lines, it's the same as doing a rotation. But now we need to mention what kind of rotation. So, what would the angle of the rotation have to be? Well, it's going to have to be 2 times the angle that it rotates through. Notice the angle that it rotates through is this 110-degree angle. It would have to be a rotation of 220 degrees, or 2 times the angle that it rotates through. Let's just make sure that was right. A rotation of 220 degrees. All right, this is not a hard lesson. We're just putting together things we learned in the past. You should be able to work the problem set for next time.